morning.
How are you all?
Doing great, man.
Yeah?
Yeah, another beautiful morning.
Are you out at the coffee shop? It is a beautiful morning. The sun's out, although I looked at the weather report. It's going to rain tonight. It's probably good. But then by tomorrow morning it'll be sunny again. How about the rest of you?
Oh, doing okay.
Hey, your mic sounds good today. Well, what week is this? Is this like week 10? I've totally lost track. I don't either. I don't know either. 10 or 11, something like that.
I think it's 11.
11. So we got 12, 13, 14, 15, 16. We got 5 weeks left. And we're going to be spending another, not today, but Monday, and then possibly also part of Wednesday, talking about graphs. And then we're going to be switching over to finite state automatons, which is a different kind of graph. So pretty much graphs from here on out. And then towards the end of the semester, there's going to be just a week or two where we kind of have nothing scheduled. And so that'll be an opportunity to talk about maybe some optional things or things you want to go more in depth on that we have talked about over the semester. So we'll figure it out. It's assuming that I don't get sick. Like I said, the rest of my family is recovering from something going around where it starts out with a couple days of a high feverish, like 103. And then they get like a little bit of a congestion. So we don't know what it is. It's just some kind of flu or cold going around. So far, I've managed to avoid it, or I've got it really, really, really mild. So, can germs transmit via Zoom recordings? I think I caught whatever your kiddo has. Maybe. Got a virus, huh? Oh, sorry. Where is it? Is it here? Is it down here? Up there. Up on your nose. Those are the worst, huh? Oh, actually, the worst is when the coughing sets in. So I thought today I would give you on Monday we went over this a little bit. I started talking about how a arithmetic expression gets turned into a tree, and then that tree can be traversed and then turned into assembly language instructions, and then those assembly language instructions can be further optimized to reduce, let's say, the number of registers being used. So I thought I would expand on that a little bit and talk more broadly about how a program is actually compiled. Let me go ahead and I'm going to turn off the music so that YouTube doesn't get upset with me. There we go. So a compiler really is just a program that humans write. And what it does is it takes in a file as input, and that file consists of the source code, and it transforms it and then outputs it into another file. That's basically all it does. And when I say it's written by humans, it's because I think there's sort of like this conception, especially when you're a beginning programmer, that all this compiler stuff is just magic, right? That somehow you hit the compile button and then something happens and then the program starts running and who knows what's going on. But really, they're just programs that people like you and I have written that just take in a file as input, the source code file, transform it into another language, whether that's assembly language or machine code or the language for like the Java virtual machine, the JVM language, and then just outputs that into a file, and then something else takes over to actually execute it. So here on the screen, I've got a block diagram showing you all the phases that a program goes through to be transformed from the source code into the target language. And I'm going to use an example, like a really, really simple language, like one where all you can do is just evaluate arithmetic expressions and assign them to variables. So your source code starts out, and the first thing it goes through is a program that's either called, and these are three names for the same thing basically, a scanner, a tokenizer, or a lexer. Those are all synonyms of each other. So the job of this particular stage of the compilation process is to go through your program and kind of tag each one of the pieces of your program with what they are. And by pieces, I mean the individual building blocks, not like the things like this is a function and this is a variable, but actually each one of the little tiny pieces. So for example, if this is the source code of my program here, it's going to output something called a token stream, and it has gone through my program and tagged each one of the things in there with what kind of thing that is. So it might look like this. X equals 3 times y plus 6, semicolon, and it has tagged the X there. And in compiler speak, that X is something called an identifier. It's a name for something. Yeah, it happens to be a variable, but an identifier is just broadly just a name for something. I'll just abbreviate it ident. And then the 3 has been tagged, and it says that's an integer, as opposed to a floating point number, or as opposed to a fraction or something like that. Same thing with the 6. It has tagged that. This y here, that's an identifier. This multiplication symbol, we might say that's an operator. The addition symbol is an operator. And then this equal sign, that's the assignment operator. And then we got a semicolon on the end, and the technical term for that is probably semicolon. So our variable assignment has been tagged with identifier, assignment operator, integer, operator, identifier, operator, integer, semicolon. It's kind of like going through a sentence that someone wrote down and identifying the parts of speech. This is a verb, this is a noun, this is a participle, this is a conjunction, right? You went through each one of those words and you tagged it with what part of speech those are. So that's what the scanner or tokenizer or lexer does. Then this token stream goes through the next phase. The next phase is called the parser. The job of the parser is now to turn that into that tree that I showed you. So it might look like this. Equals, and then x to the left. And then over here we have 3 times y plus 6. The plus would be at the top. Then we have a 6 below that, then a times, then a 3, and a y. And of course, these tags from the lexer are also accompanying each one of the pieces. assignment operator at the top, identifier, operator, operator, int, and identifier. So the parser turns it into this tree. If the parser is unable to turn it into a tree, and what the parser is working with is a set of rules about how to organize statements and function declarations and conditionals, right? It has what's called a grammar, basically. Just like in a regular natural language, the ones that humans speak, there are grammars, right? That are the rules for how to put together sentences. That's what the parser has. The parser has a set of rules that show it how to put together things like expressions and function declarations and conditionals and loops. What is the proper way to put those things together? So if it is able to transform your program into one of these trees, then the parser has done its job. If it's unable to transform it into a tree because there's a problem with your program and it doesn't match one of the rules, one or more of the rules that it has, then it generates an error. And you see those error messages on your screen when you compile your program. So something like semicolon missing, expected a parentheses, expected a declaration here. That's because it has a set of rules, and it can look at the rules and see what comes up next. And if it doesn't see that thing next, then it gives you an error message. By the way, here's what one of those grammars might look like. This one here says, an assignment consists of an identifier followed by an equal sign followed by an expression. And an expression is another expression and then either a times or a divide followed by an expression. So you got two expressions on either side with a times or a divide in the middle. And then that can be further broken down into an expression with a plus or a minus between them. And then expressions on either sides. And then an expression could be just an identifier or just an integer. And then down here are the rules for doing pattern matching. These are the lexer rules down here, and these are the parser rules up here. So the lexer rules show us what an identifier looks like, what an integer looks like, and then what white space looks like. And there's an instruction here that says any white space you see, just skip it. Just ignore the white space. So that's what the grammars for a parser and a lexer look like. Okay, this tree that comes out is called an abstract syntax tree. And then that goes into the next phase, semantic analysis. Semantic is a word that means what something means. So the purpose of semantic analysis is, now that we've got this tree, is to go through and make sure that everything makes sense. So it applies some further rules. Rules like if you want to use a variable, you must first declare it. Rules like type matching, like if you want to add two numbers together, you need to make sure they're both numbers, and you're not like trying to add a string to an object, right, or something like that, or something where you don't have instructions for how to do that. Or it could be rules like, what could be another rule? Oh, like scoping rules, like make sure that your variables are declared in the correct scope, and if you can't find a variable declaration in this innermost scope, look in the outer scopes until you find it. And if you don't find it, then throw an error about that. So that's what I mean by, does the program make sense? Are the instructions kind of like in the right order? Are you following all the rules of the programming language? So if the program does in fact make sense, then it goes on. You still got an abstract syntax tree going through. All it does is it just kind of like analyzes the tree, just makes sure that everything's in the right spots. And then it finally goes into code generation. And this is where the target language is actually produced. So it walks that abstract syntax tree. I showed you a little bit about that last time. And then as it's walking the tree, as it's traversing the tree, it's emitting out the target language. Emit, like it's at, writing it to the file. And then finally, it could go through a phase of optimization. That's where you can do things like reduce the number of registers being used or eliminate redundant instructions. There's just like, this is actually primarily where research in compilers are being focused right now, is in optimization. Looking at your program and figuring out, are there ways we can make it run faster? Some common optimizations are inlining code. If you have a function in your program or a method that's really short, maybe just a couple of statements, you could actually take the body of that function or method and then plug it right into where the function is being called. That eliminates the call to the function and the overhead associated with it, and it just executes the instructions. Inline. We can also do something called a loop unrolling. That's where if you have like a loop that goes from 1 to 10 and it does a few things inside there, we could turn that not into a bunch of loops where it has to go back up and execute instructions again, but actually unroll the loop so it turns it into just a long sequence of instructions. It's actually faster to execute than a loop because it doesn't have to jump back and calculate the destination address of where it has to go back to. It just simply executes the instructions from top to bottom. You could do things like taking advantage of, what am I trying to say? I've seen optimizations where, let's say you're trying to fill in an array. So you've got an array and you're filling in each of the values. Well, it might be faster for the processor, the particular processor you're working on, to fill in 2 or 3 or 4 values simultaneously. Because that's just the way the processor works. Maybe it works on 32-bit or 64-bit words more natively than it does on individual bytes. And so if you can load that array in larger chunks, that can go faster. You can also reorganize some of the instructions. If you've got 2 instructions, or maybe 2 or 3 or 4 instructions, and let's say these 2 instructions have to go in order, but this 3rd instruction could go either before or after because it doesn't depend upon these 2. Maybe it's faster to move it up here. Maybe it's faster if you've got something like hyper-threading on your processor to execute these 2 instructions on one thread and this instruction on another thread, right? So they can go in parallel with each other. There's all sorts of stuff that can be done to make your program go faster. And I guess the upshot here as a programmer is don't concern yourself too much with trying to outthink the compiler and go, most of the time, the optimizer is going to be better at organizing your code than you are. Most of the time. Not all the time, but most of the time. So for example, in some programming languages, there's the plus plus operator. Like x plus plus to increment x. Or you could write x plus equals 1. Or you could write x equals x plus 1. Turns out for most compilers, that generates exactly the same code. Doesn't matter which one you use. They're all the same speed. So pick the one that works best for you, and then don't worry about which one's faster. Okay, so that's generally how a compiler works, is it goes through these phases. Your program is transformed, turned into a data structure, and then that data structure is analyzed and further transformed. And then finally, that data structure is used to produce the target language. If you take a course in compiler writing or compiler construction, hopefully that's like an upper division course you might take at a 4-year university, then you'll write a program that goes through all of those phases. By the way, let me show you a little bit here. So I wrote out this grammar, and we can actually run this grammar and see what it does. So I'm going to say here, I'm going to test out this rule. And then if I type in x equals 3, we can see over here that it has produced this tree with assignment at the top an identifier x, and then an equal sign. And it says null here because I don't have a rule that says specifically what to do with the equal sign. And then I got an expression which has an integer of the value 3 below it. So this is the tree that it produced. Let's do something a little more complex. Let's go x equals 3 plus 1. So here's the tree that it produced. We've got an assignment statement, x over here on the left, equal sign, and then 3 plus 1. And you can see that 1 is actually a type of expression, and 3 is also an expression. And then this 3 plus 1 is also an expression. Okay, let's do something more complex here. Let's put in a times 2. So with this, we should see the plus at the top and the times down below, because the times has to happen first. And that's in fact what we see here. We've got the plus here, and then down below we have the times. Here's 1 plus 2. And let me swap in a variable here, and then let's do like plus 5. So 3 plus 1 times y plus 5. So we got assignment at the top, x equals, and then here's a plus. And then down here is also a plus. And we've got 3 over here, times, and then 1 and 5 over here. Y, I mean, and then 5 over here. Okay, so we got 3 plus 1 times y plus 5. So you can see what I'm doing is I'm walking this tree. I'm going from starting from here, and then I go 3 plus 1 times y plus 5. Now we can even do a more complicated grammar. This is one that looks more like a regular programming language, where you got things like this. Let's do int y, y equals a plus b. So I've got some variable declarations on the outside here, and then I got a function declaration. And then here's the tree that got produced. So we got program at the top, we got a variable declaration statement, and a variable declaration statement. A statement is basically something that ends with a semicolon, right? So we've got int x semicolon and a double y semicolon. And then over here on the right-hand side, we've got a function declaration. We've got int add parentheses, int a comma, int b close parentheses, open brace, int y semicolon, that's a statement, and then y equals 3, a plus b, semicolon, and then there's our closing brace. So what happens if we have a syntax error, like we miss a semicolon? So then it's unable to build the tree. It says right here, missing a semicolon. That's because our rule says that after we have a variable declaration statement, there must be a semicolon. So the compiler says, I'm expecting to see a semicolon here, and I don't see one. So that's an error. And then so what this doesn't have at all is any kind of semantic analysis. So it doesn't complain if I put like int z here and then y equals a plus b, because this is a grammatically correct program even if it is not semantically correct. There's no semantic analysis here. This is just purely grammar. It's kind of like saying, the cow jumped over the moon, right? Grammatically correct, but not really sensical. So if I just put something like int semicolon, or then we got all sorts of errors here. If I miss a brace, I got an error way over here. It says we hit the end of file before we saw the last thing we were supposed to see. All right, so that's generally how the parsing and the scanning goes. Oh, by the way, one last thing to show you is I can go here to Tools and I can say, where was it here? Tools, Generate Recognizer. And then if I look at, here is the Java code that this tool produces. So you write the grammar, you write the rules for the lexer and the parser, and then it writes the Java code for you. So I didn't write this. This tool wrote this for me. And then all this stuff in here, all this stuff here is actually sort of a compressed version of the grammar rules. And then the parser doesn't look much different. I don't know what all this stuff means, right? But this is all code that it wrote. There's a lot of stuff in here. So these kinds of tools are more generically called a compiler. It's a programming language for writing compilers. It's basically this is the language, and then you run the compiler, and it will compile this language into your target language, which in this case is Java, and it writes the code for the compiler. All you have to do at this point is take these Java source code files and connect them together inside of a main, have it open a file for reading, push that file into the lexer, take the output of the lexer, push that into the parser, and then from there you need to do your semantic analysis and your code generation. So you then take the output of the parser, you've got this nice data structure, and then it's up to you to now start walking that data structure and emitting the code as you go. So that's what a compiler does, and hopefully you'll get to use one of the days when you take a compiler construction course. Any questions? You guys have all been kind of quiet.
What programming language was the grammar in?
Oh, this is one called Antler. A-N-T-L-R. It's right down here. I'm sure it's an acronym for something. I don't remember what it is. So I am using the IntelliJ Integrated Development Environment, or IDE, and there is a plugin that you can just download and plug right into IntelliJ called Antler, and then it puts in the compiler for you. It can generate code in not only Java, it can output C code. I don't know. There's a variety of backends where it can produce the compiler code for you in a variety of languages. I know it can do C and a couple others. Your eyes glazed over once you saw the file's output code. You don't worry.
So
You don't
what?
worry about that, right? That's the compiler wrote that for you. You don't worry about what it is. All you have to do is learn how to call it and how to get the output from it. Don't worry about what it actually looks like. Oh, sorry, I interrupted someone.
No. So what this is doing is it's compiling from Antler to Java.
Yep.
That's what. Okay.
Yep.
And is that something you could do with any language with one of these compilers? Write a program that compiles from any language to another language, like to a
Yeah.
compiled language.
Yeah. So, like, if you wanted to, well, so what's probably going to happen is if you take a compiler construction course, they're not going to have you like write a compiler for Java. That's too complicated. What they might do is say, here's a language that has a very simple set of rules. Like you can create variables, you can create functions, you can call functions, you can do loops, and like that's basically it, right? Very, very simple language, and they say you're going to write a compiler for that. So the first step is to write the grammar for the language. What are all the rules? Which is what I got on the screen here. And then they'll say use a tool like Antler to turn that into whatever your target language is. So if we're all comfortable programming in Java, they'll say, okay, we're going to target Java, and then the rest of the compiler we're going to write in Java. So what'll be the final result will be a Java program that can take the source code of this toy language that you're writing a compiler for, and then outputting, let's say, assembly language for, like an AVR processor, or maybe even if you took like Computer Science 10, you might have used like the PEP8, if you remember that, like that toy assembly language. So it doesn't correspond to any real assembly language, but you could run it on an emulator. And so maybe your compiler, which is written in Java, can input a source code program in some toy language, we'll call it ABC language, and it outputs PEP8 assembly language instructions. So a Java program that takes in ABC language and outputs PEP8, right? So the compiler doesn't have to be written in the language that you're either pulling in or targeting. It could be in a third language. Is that what you were asking? So you could,
Yeah.
you could go and you could download the grammar for existing languages. You could download the grammar for Java. You could download the grammar for C or Visual Basic or whatever, and then you could produce your own compiler for that language.
What language are compilers generally written in?
Oh, anything. The Java compiler is written in Java, believe it or not. The a lot of times, the compiler for a particular language is written in the language that it targets. So, or written in the source code language. So, like the C compiler is written in C, the Java compiler is written in Java, the PHP compiler for doing like web-based development, I think, is written in C.
That's a real which came first, the chicken or the egg situation.
Yes, definitely. So there's actually a whole process called bootstrapping a compiler, which is how can I write a compiler in a particular language if I don't have a compiler for that language yet? And so maybe the first compiler you write is written in assembly language because you happen to have an assembler. And that might not be the full language. That might be just enough to be able to get another compiler running in that particular language. So you might write, let's say you're writing a C compiler, but you don't have a C compiler to write a C compiler in. So you might write the very first one in assembly language, and maybe all it can do is just declare variables and do some rudimentary loops and get input from the keyboard and output to the screen, right? Maybe that's all it can do. So you got a really small compiler that you've written in assembly language yourself by hand, and then you run that program, and the input to that is now a slightly bigger C program that can do a little bit more. Maybe it can now do, all three kinds of loops instead of just one kind of loop. And maybe you can now do more complicated functions. Maybe now you can do recursion, which you couldn't do, maybe couldn't do that before. And so that second compiler can then be used to maybe produce a third compiler that can do the full language. So it is kind of a chicken and egg problem. You have to start with a small compiler and then build up from there to get your full-featured compiler. And that's how you ultimately can get a compiler that's written in the language that it compiles. Python is written in C. In fact, it's called CPython. And there's also a JPython, which is the Python compiler written in Java. And there's also a JS Python, which is the JavaScript compiler for Python. Processing, which is maybe a language you might have used in your introductory course, it was written in Java. And you might have noticed that when you write your processing instructions. Even though it doesn't quite look like Java, you get Java error messages. It's because there's actually a Java compiler doing the work in the back end. Which drove me crazy. Like, how are beginning programmers supposed to understand these weird Java error codes coming out? What else? There's tons more. I'm just trying to think off the top of my head what languages compilers tend to get written in. So you could write a compiler in pretty much any language. You could write it in Python, you could write it in PHP, you could write it in JavaScript, you could write it in C, Java, whatever you want. All it is a program that takes in your source code language. It's just a text file. And then it turns it into that data structure, and then it outputs the output language.
Real quick,
Mm-hmm.
how would the compiler run on, like, if you have a Python compiler, how would it run on if it doesn't have a compiler itself?
So if your compiler was written in Python?
Wouldn't you need a compiler to compile the...
Yeah, you'd need your Python compiler already ready to go. But let's say you wrote a Python compiler that compiles C code into assembly language. So it's assuming you have a way to run the Python program.
Okay, thank you.
If you didn't, of course, you got a different problem here. So you could write a compiler in JavaScript, and then all you need is a web browser to run it. Oh gosh, I was going to say one thing, and then I totally forgot what it was. Well, it'll probably come to me tonight at some point.
Did it have to do with compilers?
I think it did, although it was starting to segue into the next stuff we were going to do. Nope, don't remember. It's totally gone now. So a big part of the compiler is that abstract syntax tree. So let's talk a little bit more about trees in general. So trees are a special kind of graph. They have a root, which is usually up at the top of the tree. And they have leaves, which are down near the bottom. The vertices of the graph are typically called nodes when you're talking about trees. And a tree is also acyclic, which means there's no cycles in it. The tree just always goes downward, right? There's never any link back up to the top. Then it's not really a tree anymore. When you're talking about a particular node, usually a node has a value in it, and then if it's a binary tree, it has exactly one left branch and exactly one right branch. Not all trees are binary trees. In fact, we saw an example here where we've got a node that has a whole bunch of branches coming off of it. That's okay. It's still a tree. It's just not a binary tree. So here's a tree that I produced. Just got a bunch of fruits on it. We got mango as the root. I don't know why I picked mango as the root, but there you go. And then we've got orange and cherry below that, and then strawberry, apple, peach, watermelon, grape. They're not in any particular order. So we can do three kinds of traversals on this. There's one called a pre-order traversal, an in-order traversal, and a post-order traversal. So I wanted to show you this picture of a node because a tree is really a recursive data structure. This is the whole tree right here. The root consists of a value, which is mango, and then a left branch and a right branch. And so does every other node in the tree, except for the leaves at the bottom. Like orange here has a value, a left branch, and a right branch. Cherry has a value, a left branch, and a right branch. So this is a tree, starting at mango. This is a tree, rooted at orange. This is a tree, rooted at cherry. So we got a tree that consists of two smaller trees. And even those two smaller trees consist of smaller trees. So strawberry is itself a little tiny tree. Apple and peach is a small tree, as is just peach. Watermelon is a tree, and grape is a tree. Okay? So if you want to traverse this tree, all you have to know is what to do at each node, and then just assemble it all together. So for a pre-order traversal, you're going to start at the root, and then you're going to follow these instructions. For a pre-order traversal, you're going to output the value. So we're going to output the word mango, and then we're going to descend left. We're going to go this way, and then just repeat. Output the value, descend left. Output the value, and then attempt to descend left. But there isn't one, so then we're going to descend right. Well, there isn't one, and so then we're going to back up, and then remember the last thing we did for orange was descend left. Now we're going to descend right. We're going to output apple, descend left, and do peach. Go left, there isn't one. Go right, there isn't one. So back up, go right, there isn't one. So back up, and then go down this side. Okay? So let's try it here. For a pre-order traversal, we'll get mango, then orange, then strawberry. Okay, so we descended left. We try to go left, nothing there. Try to go right, nothing there. So we go back up, and now we descend right. And we get apple, then peach. Okay, so we're done here. Try to go left, nothing there. Try to go right, nothing there. Come back up to apple, try to go right, nothing there. So then we come back up to orange, and then we come back to mango, and now we go to cherry. Then watermelon, and then grape. So that's called a pre-order traversal. Every time you get to a node, you output its value, and then you descend left, and then you descend right. For an in-order traversal, you're just going to rearrange the order in which you do things. First, you're going to descend left, then output the value, then descend right. So for the pre-order, you outputted the value first. For an in-order, you output the value in the middle. And then you can see later on we're going to do post-order, you output the value after you descend. Okay, so for an in-order traversal, we are first going to descend left. So we're not even going to do mango yet. Then we're going to get to orange, and we're not going to do orange yet. We're going to descend, and then we're going to do strawberry. Okay, now we're going to come back up, and as we cross from left to right, that's when we output the value. So what comes next after orange? Is it going to be apple or peach?
I would say peach.
Yep, it's going to be peach. Then apple. Okay, what comes after apple?
Mango.
Mango, very good. Okay, then watermelon. Then cherry. Then grape.
Isn't that kind of weird having the root in the middle like that?
No, it's just the way the in-order traversal works. So with the in-order, the root will end up in the middle, and all the stuff to the left will end up on the left side, and all the stuff to the right will end up on the right side. So notice.
Gotcha.
that-
Now I can see why that's
yeah,
useful.
Yeah, so mango's here, and then strawberry, orange, peach, apple were all the stuff to the left, and then watermelon, cherry, and grape were all the stuff to the right. And then finally, post-order traversal. We're going to descend first and then output the value. So we're going to start at mango, descend, descend, and then we're going to do strawberry first. Okay, and then we back up, and then we come to apple, but we're going to descend first, and then we'll do peach. Then we'll do apple. Then orange. What do you think comes next?
Watermelon.
Very good. Watermelon. Then grape. Then cherry. Then mango. So a post-order traversal, the root comes last. With pre-order, the root comes first. In order, the root's in the middle. And post-order, the root's last. So what does this have to do with compilers? Oops. Here's our expression. We can turn that into a tree. We have equals, and then x plus times 3y, and then 6. So let's do a pre-order. Remember, pre-order means output the value of the node first, then descend left, and then descend right. So this will come out to be equals x. Right, so we went this way, and now we're going to go this way, plus, then we're going to descend, times, then we're going to go down to 3, then we're done with 3, so we're going to come back over to y, and then we're done with y, so we go back up to times, then we go back up to plus, and now we come down to 6. And then there's nowhere to go from there, so we go up, and then we're done. Let's do an in-order traversal. So in order, we start here. We're going to descend, and then we'll do x. And then as we come up out of x and cross over to the plus, that's where we'll do the equals. Then we come down here, and we do 3. Then times, then y, then plus, and then 6. And look at that. When we do an in-order traversal, we basically get the same thing back.
We get it in order.
Yeah. And if we do a post-order traversal, we'll get x first, then 3, then y, then times 6 plus and equals. Okay, so what good are these? Well, each one of these are useful depending upon what kind of language you are outputting to. Like if I'm doing a, let's say this is a C program and I'm outputting Java. Well, C and Java have very similar syntaxes. When you write out a mathematical expression, you do it in what's called infix notation, which means our operators go in between, like 2 plus 3. It's the way we humans have been writing mathematical expressions for centuries. So if you are compiling one language to another language, and those two languages are similar in the way that they deal with things like expressions, you'll want to use something like an in-order traversal, because both C and Java have the same sorts of way of writing expressions. If I'm emitting assembly language, I'll want to do a post-order traversal, because this happens to match the order in which I would emit the assembly language instructions. I'd do something like load X into register 1, and then load 3 into register 2. Load Y into register 3. Multiply register 2 and register 3 together. Load 6 into register 4. Add register, multiply, we'll put this into register 4. This is going to go into 5. Then we'll add register 4 and register 5 together and put the result in register 6. And then finally we'll do a store register 6 into register 1. All right, so basically, as you walk your post-order traversal from left to right, you're just emitting assembly language instructions as you go. And then, what good is a pre-order traversal? Well, it turns out there are programming languages in which the operator always comes first. Those are typically called functional programming languages. And actually, they're not that strange. If I was to replace these operations with function calls, let's say the equal here, I'll call that let, which is a statement from like BASIC. You say let x equals 2, right? Which is basically an assignment statement. All right, so if I just turn each one of those operators into a function call, then it looks kind of like what you would write in Java. You'd have like a multiply function, which takes in 2 parameters, and the result of that becomes the first parameter to add, And then the result of that is what gets stored into X using this let function. And if I was to do this in a language like Scheme or Racket or Lisp, it would look like define X plus multiply 3y 6. So there are uses for each one of the different kinds of traversal, depending upon what your target language is going to be, what kind of syntax it needs. You know, you got a language that is written in infix notation, use an Inorder Traversal. You got a language that's written in prefix notation, in which the function calls always come in the front, then you use a pre-order traversal. And if you're using a language in which the operators always come at the end, so operands first and then operator, then you use a post-order traversal. And assembly language happens to work very much like a post-order. There's other languages like Forth and PostScript and Factor, which are postfix languages in which the operator comes at the end. Also, if you've ever used a Hewlett Packard calculator, I have one down here somewhere. Nope, not in that drawer. Nope, not in that drawer. I forgot where I put it. When we were doing our probability stuff, I had that calculator out, and occasionally I would flash it on the screen. And, oh, I forgot where I put it. Oh, maybe it's in this drawer down here. Ah, yeah. So this is a Hewlett Packard calculator, and they're well known for being postfix calculators. So when you turn it on, you get, can you see this on your screen here? You get this stack. And so if I was to do 2 plus 3, I'm going to move out of the screen here so it doesn't focus on me. I'm going to go 2, enter, and then 3, enter. And you can see it puts the 2 and the 3 on the stack. And then I go plus, and it replaces those 2 and 3 with a 5. Okay. If I want to do like 1 plus 2 plus 3, I go 1, enter, 2, enter, 3, enter, and then I go plus plus, and then it replaces that with, what was it, 6. Okay, so if I want to do, let's do like 3 times 2 plus 6, I would go 3, enter, 2, enter, times, and then 6, enter, and then plus. And then I got my final answer. What was that? 12. And I don't actually have to enter after everything. I can, if I want to do, 1 plus 2, I can actually just go 1, enter, 2 plus, and then you don't have to do the enter after that last one. It's a little bit of shortcut there. So the nice thing about this stack, when I was doing those probability questions, is I can work out the numerator first and push that onto the stack. Then I work out the denominator and have that on the stack, and I can see both the answers. I can see both the numerator and the denominator at the same time on the stack, which was nice because that way I could just transform what I saw on the screen here to what you saw on my iPad, and then I just hit divide, and then it divides the numerator by the denominator very, very easily and quickly. So a lot of engineers like these Hewlett Packard calculators because of the postfix notation. It doesn't take very long to learn how to translate infix to postfix, but it is nice because you can see all your intermediate calculations stacking up on here. And then you can just, at the very end, if I have to divide a whole bunch of stuff or add them together, you just go plus, 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 or divide, divide, or divide plus, and then boom, it comes up with your answer. So like over here, if I was to do the order traversal, what I get here is a postfix expression. Let's do another one. Let's do like, well, let's do the one I just had. On there were 3 oops, 3 times 2 plus 6. And so the way this works is every time I see a number, I push that onto the stack. And every time I see an operator, I pop 2 values off the stack, do the operation, and then push the result back onto the stack. So here I'll have 3 on the stack. Oh, whoops. I don't want to do 3 times 2 plus 6. What I have to do is I have to transform that into a postfix expression. So this becomes 3, 2 times 6 plus. Okay, so I push 3 onto the stack. Then I push 3 and 2 on the stack. Then I see the multiply, and I replace that with 6. Then I push 6 on the stack, and then I see the plus, and I come up with 12. Let me just move that over. And let's say I had, let's do a slightly different one. Let's do 10 plus 5 times 3, okay? So this becomes 10, 5, 3 times plus. So 10 goes on the stack, then 5 goes above it, 3 goes above that, and then when I hit that multiply, I'm going to replace that 3 and 5 with 15. And then when I encounter the plus, I'll take the 10 and 15, add those together, and replace them with 25. So let's try that out on the calculator right here. So I'm going to go 10, enter, 5, enter, 3, enter. So I've got the 10, 5, and 3. Now, in this case, the stack is going upward here, so I've got them kind of backwards from what I showed you on the screen. So I got 10, 5, and 3. The 3 is on the top of the stack, even though it's on the bottom of the screen here. And then I'm going to hit times. So you can see that 5 and 3 got replaced by, what was it, 15? And then I'm going to hit plus. Here's the plus key. And I get 25 there. And this is actually a complete programmable calculator. It's got its own little programming language. You can go into a programming mode, and it's got its own little stack-based postfix programming language, and you can write little applications for this. It's not something I've gotten into myself. I just like the postfix notation on it. And had to make myself a little cheat sheet about all the operations. I gotta get out of the screen here. Come on, there we go. A little cheat sheet. Okay, well, believe it or not, that's about all I had for you today. It's just an introduction to the stages of compilation and how those programming languages get turned into a target language. Normally, today is Wednesday, and we would have an assignment, and if I recall, I don't even have one of those for you either. Today is just an easy day.
Wow.
Let me just double check that that's correct. Nothing as far as an assignment go. Easy week. Let's see, what do we got here? People are voting on, should I do A star, depth first search? We'll do some of those graph algorithms next week. Shortest path, spanning tree. Haskell, you're right, is a programming language that it's a functional programming language, but it also does infix notation in some places and prefix in others. Haskell's a very interesting language. I mean, there's the functional aspect. So first of all, for you don't know, a functional language is one in which the function, something that takes in some inputs and produces an output, is the fundamental building block. Whereas like in a language like C or Java, the fundamental building block is the statement. And a statement like x equals 5 has what's called side effects. So x is being stored somewhere over here, and the value 5 gets put into it. And later on in your program, you can say x equals 10, and the value of x gets replaced by the number of 10. It seems very natural to people who have been programming for a while in statement-oriented, what's called procedural languages. But in a functional language, the fundamental building block is the function. You get inputs coming in and an output coming out. And the idea there is that there's no side effects, that a function is a self-contained unit. A function can't affect a variable somewhere else. So if I got a function called add that takes in two values and produces a result, that add function can't like change the value of x somewhere over here. What that means from a programmer's perspective is that functional languages are very reliable. Reliable in the sense that I can predict what's going to happen. If I have a function called add, and I take the value 5 and the value 10 and I put it in, I'm going to get the 15 out. No matter, every time I call that function, I will always get a 15 out if I put a 5 and a 10 in. Whereas in a procedural language, you might put a 5 and a 10 in, but it might assign a random value to the value x as a global variable, as a side effect. And so you never know what this function is going to do because it has a side effect with a random mutation. Whereas a functional language, you can't do that. There's no global variables. And so coming from a procedural language, you might go like, what's the use of that? If I can't mutate variables, how can I write programs that do anything useful? It's just that functional languages have their own mechanisms for doing those sorts of things. So Haskell is an interesting language in that one of the features that defines it or separates it from others is that you can write functions that produce an infinite amount of output. So like I could write a function that takes in let's say a value, let's say 100, and then its output is going to be an array of the numbers 1 through 100. Okay, no problem. I could write a function to do that. But I could also write a function that takes in no value at all and produces an array from the numbers 1 to infinity. And as a programmer, you might go like, well, how could I possibly return such an array back to the caller, right? It's going to take an infinite amount of memory. Well, the answer there is that Haskell doesn't actually produce the array when you tell it to. It produces the array when it needs to. So if you call this function and it produces an array of an infinite number of values, but then you never do anything with it, it never bothers to actually allocate the memory for the array. Okay, so let's say I call this function, it produces an array of an infinite number of values, and I say print out element number 50. Well, it doesn't have to instantiate the entire array. It only has to instantiate element number 50 of this array. And so it doesn't use up a whole lot of memory. It only uses up like one integer's worth of memory to do that. So with this in mind, it's possible to write programs that start with essentially an infinite amount of data, and then you filter it down to just the stuff that you need. It's like a totally different way of, and some of these languages aren't necessarily because you write real applications like web browsers and apps on your phone with it. They're, one of the goals is maybe to explore different ways of writing programs and explore different ways of analyzing what programs are supposed to do, and as a result, write different kinds of programs to do them. And so many times Haskell exists because it's just an exercise to like get your brain to think differently about writing programs. There are other languages like that, like Racket and Scheme. Again, you think differently about how you construct your programs. In functional languages also, functions can take in a function as input and also produce a function as output. So you can actually write functions, right? You can write a function that takes a function in, transforms it, and produces a function that comes out. And essentially, that's what a compiler does, right? Is you've got this program, which is basically a function, a giant function, and then you've got another function that takes that and transforms it and produces another program. Right, so at its core, really, a compiler is just a giant function whose input is a program and its output is another program. So some of the very first compilers were written in functional languages because that was just a natural thing for it to do. Some of the very first experiments in artificial intelligence was also written in functional languages because, again, that was for back then, that was a very natural thing for it to do. You got all this like input coming in, and then you do something to it, and then you got an answer coming out. Like if you want to do speech recognition, you got like a sound file coming in, you do a transformation on it, and then you've got an answer as to what that word is coming out. So functional language is also great for programming language practitioners because of its reliability, because of its predictability, it's easier in a functional language to prove that a particular program works correctly. Because you always know for a given input, it's going to produce a given output. Whereas in a procedural language, you're never quite sure because there's side effects. A function might have an input, produce an output, and might also change a variable somewhere else. Now, that being said, functional languages do need to be able to be used for real programs, and real programs do have side effects, real programs do have global variables, and so most functional languages have a way of affecting global variables because you just kind of can't get away with it. But when you learn a functional language, first you learn the core parts, which have nothing to do with global variables, nothing to do with state, nothing to do with mutating variables. You just learn how to write programs using nothing but functions, and then you can extend that out to writing programs with state, with mutation. Some universities start you out with a functional language. You don't learn JavaScript or C or Python or Java first. You learn something like Racket or Lisp first or Scheme first. They think that it helps you not learn bad habits right away because you don't have global variables. You never get in the habit of using them. Right? And programmers often say, like, don't use globals as much as possible. Get away from globals. Just stay away from those things because it makes your code brittle. It makes this part of the code dependent upon this part of the code because there's an intermediate global variable that's used to pass values back and forth. You can't then take this function and separate it from this one because there's a dependency on this third variable. So get away from global variables. Well, in functional languages, you're not shown that you can even have them in the first place. So you never develop the habit of using them. Functional languages also tend not to have things like traditional loops. So again, you go like, well, how can I write a program without a loop? Well, there are other mechanisms for doing it, like recursion. So you learn recursion like in week number 1 or week number 2 as a way to do a loop. And then later on, you go like, well, you know, there's these things called loops that count from 1 to 100. We'll show you how to do that. But now that you know recursion, you don't have to like try to shoehorn recursion into your understanding of loops. Now you have the reverse problem of trying to shoehorn loops into your understanding of recursion. All right, I hope you take a programming languages course at some point and learn about these different kinds of languages. Oh gosh, there's other ones. There's like Prolog, again, an old language, but Prolog was designed at a time when computer scientists thought that computers could eventually solve problems for you. Like you would just describe the problem to the computer, and then it would figure out how to solve the problem. And so with Prolog, what you can do is feed it a bunch of facts. Like, Joe and Sally are siblings, and Fred and Sam are also siblings. And then you can say like the father of Fred is make up a name, and the father of Sally is, so you're feeding all these facts about relationships between people, for example. And then you can ask it questions like, who's the grandmother of Sally? And are Fred and Sam cousins, right? So you can feed it facts, you can feed it information about relationships between people, and then it can then infer more relationships between them. So the idea is that you could feed it a whole bunch of business facts, and then from that it could infer things about your business. So it's almost kind of like artificial intelligence, kind of. And this was back in the 60s when they were exploring that stuff. Languages like Fortran, again, old languages designed specifically to do mathematical computations really quickly. So Fortran has things like arrays and variables, and it's got loops, but arrays are always fixed size, right? Once you declare an array to be like size 10, it's always 10. In fact, you can never make an array that's a variable size. It's always got to be a fixed size. The purpose there was that the compiler then could learn everything about the language, or everything about the program ahead of time. It could know exactly how much space this language was going to take up in the computer's memory. You didn't have recursion. I think you barely even had functions in Fortran. So, which meant if you don't have functions, then you can't have functions that call other functions, and you can't have functions that call themselves. And so it means you can analyze the program and know, okay, this program is going to use exactly 150 bytes of memory. And back then, in the 1960s and 1970s, every byte was really valuable. So you could say like, well, I've got this program that's going to use 150 bytes, and I've got this other program that's going to use 280 bytes, and I know that I can fit both of those programs in the computer's memory simultaneously because the whole whole computer only has 1 kilobyte of memory. So I know I can load both of those in at the same time, and therefore I can run one program and then the other program, one after the other, without having to load one, unload it, load the next one, unload it. Also, by having things like arrays of a fixed size, it was good for what was then called supercomputing, which was a computer that maybe had multiple processors on it, or processors that could work on chunks of an array simultaneously. So if you wanted to do what was called vector calculations, like I've got this an array of numbers, and let's say I want to double all the numbers. I want to take all the numbers and multiply them all by 2. Well, I could do that to element number 0, and it doesn't affect what's going on in element number 10, right? I'm just doubling everything. So I could load that into what's called a vector processor, and it could do all of them simultaneously. These days we would call that like symmetric multiprocessing or GPU calculations, right? But back then it was called supercomputing. So Fortran was great at that because you had arrays that were basically vectors, and you could load them to a vector processor and then do them faster. So Fortran was great for that. These days, most engineers don't use Fortran anymore. They use like C or Java or Python. Python is actually taking over as being a mathematical computation language. Anyway, I'm just blabbing here. It wasn't until I graduated from university that I really started to develop an appreciation for the vast variety of programming languages that are out there. I came up with this saying that every programming language exists because some programmer decided that every other programming language that existed at the moment was deficient in some way. Right, so this programmer looked at all the programming languages that were out there and said, none of these do exactly what I want, so I'm going to make a new language that does exactly what I want. Some students always ask, like, why don't we just have one programming language? Why are there so many? Why isn't there just one that does everything? Well, because it's like Why don't we have just one kind of pen? Well, because everyone wants a pen that's a little bit different, right? Some people want pens that are made of plastic. Some people want pens that are made of metal. Some of them want them in blue and black and red. Some people want felt tips. Some people want ballpoint tips. Some people want pens that can write upside down. Some want pens that can write underwater. Some want pens that can work in space. So pen designers always think, well, every other pen out on the planet just is deficient in some way, doesn't have some feature that I want, so I'm going to make a new pen. Sometimes we just make a pen because they're pretty. Sometimes we make a pen just because we want to try something out, not because we want to make like a new functional, new kind of pen, but we're just like, well, I wonder what would happen if we put two tips on this, one over here and one over here. Well, turns out that's somewhat useful. Not always, but somewhat. So we have lots of programming languages because we have lots of people who want different things. And some languages are very practical, kind of like very serious languages, and some of them are fun languages. Some of them exist just to have fun with them. Google around for esoteric programming languages, and you'll come up with a whole bunch of fun languages. Languages that exist purely just to be goofy. Maybe I'll show you one or two of them here. This is one of my favorite ones here, Bfunge. Bfunge is a two-dimensional programming language. You program it on a grid rather than, statements that follow one another. And so the nice thing about it is loops are literally loops. You write loops by just, having your program counter go around in a loop. So this is hello world written in Bfunge. Starts here, decrements, comes over here, and eventually it's going to emit the letters hello world to you. Yeah, here's another interesting one. Oops, I didn't mean to do that. LOL code right up here. It's supposed to be a language that was written by cats. Here's a Piet program. Hello world written in Piet. Shakespeare, programming language. Programs in Shakespeare are written to look like Shakespearean plays. So you have your stage directions, and those are basically variable declarations. So here's hello world written in Shakespeare. And you may look at this and you go, well, that's a lot of code, right, to just print out hello world. The vast majority of this is just comments, really. It says up here, where does it say it? Up here, it says, any code after the colon is considered a comment, right? So, you see a colon in the code, anything after that is just a comment. So a lot of the stuff here is actually just comments. The white space programming language uses tabs, spaces, and enter. So, here's a white space written with a tab, space, and line feed so we can see them. But the actual language itself is just nothing but blanks.
Looks like a Morse code.
Well, it does. This is because they've visually shown here each one of those things. But if you actually look at some sample code, where do we got sample code? There's an official whitespace website. What do we got here? Official website of whitespace. Here we go, examples. Here's Hello World. Oh, let's go away here. So, oh, that's actually running it. I want to see the source code. Let's go back a bit more. Let's go whitespace corpus. No, that didn't do what I wanted either. Oh, I'm getting nowhere with this. Yeah, I want to see the source code. Oh, here's the, yeah, I can just highlight this. Here's the source code. It's just a bunch of spaces. I'm just highlighting it so you can see them, right? But this is the source code. So here's the source code for Hello World.
This looks like something could be used for spies, no?
Maybe. There's basically a proof out there that says that the minimum number of symbols you need for a programming language is 3. And then you can represent any programming language, any operation in a programming language can be represented as combinations of those 3 things. And so that's basically what whitespace is doing, is the 3 symbols are space, tab, and return. But you could use like ABC, you could use fish, duck, and aardvark. You could use any 3 symbols you wanted, and then you can write any program in any programming language using just the 3 symbols. Anyway, I've blabbed enough here, so. Like I said, next time on Monday, we'll go over some fundamental graph algorithms like shortest path and spanning tree. We'll do A star if there's some time. And then on Wednesday, we might be doing more graph stuff, or we might start segueing into finite state machines. So, and there's no programming assignment this week, so you have it easy. Any questions, comments before we take off?
I guess not.
No, we're good. Okay.
Thank you, Professor. Have a good day, everybody.
You too.
Yeah, thank you.
Have a good week.
Thank you, it was fun. Thank you.
I like bringing this fun stuff in there. We could do boring graph stuff, or I could talk about this fun stuff. Okay, have a good weekend, everyone. Take care. Hope you have some fun poking around these esoteric programming languages. Take a few moments out of your weekend to poke around a little bit. Talk to you later. Bye-bye.